Good morning, afternoon, everyone. Today, we are going to dive into the world of electronics design. Our focus will be on understanding the fundamental concepts of analog and digital signals, converters, and a structured approach to problem solving in electronics. Let's get started. We begin with a brief history of cellular phones to illustrate the impact of technology scaling in electronics. Early mobile phones were bulky and often required a bag to carry around, hence the term bag phone. Over time, analog phones became smaller, but they still suffered from poor battery life. Today, we have compact digital phones with long battery life and integrated features like cameras, GPS, and Bluetooth. These advancements are possible due to increased integrated circuit (IC) density. Here we see examples of an early Uniden bag phone, a Nokia analog phone, and a modern Apple iPhone. Now, let's classify electronic signals into two main categories: analog and digital. Analog signals can take on a continuous range of values, representing variables like temperature, pressure, and sound. Digital signals, on the other hand, appear at discrete levels, typically represented by binary values, 1 and 0. Understanding these differences is crucial for designing and working with various electronic systems. Let's delve deeper into the classification of electronic signals by looking at two main types: analog and digital signals. This distinction is fundamental in understanding how different electronic devices operate. Analog signals. Analog signals can take on a continuous range of values. Think of them as smooth, flowing waves that can represent real-world phenomena like temperature, sound, and light intensity. For example, the voltage output from a temperature sensor varies continuously to reflect the temperature changes accurately. To help you visualize this, look at Figure 1.7a. It shows a continuous analog signal. This type of signal smoothly varies over time and can have any value within a certain range. In practical terms, this means an analog signal can represent infinitely many possible values within its range, making it ideal for natural, real-world data. Digital signals. Digital signals, on the other hand, can only take on specific, discrete values. Typically, in digital electronics, we deal with binary digital signals, which can be either a logical 1 or a logical 0. These two states are represented by two distinct voltage levels. For instance, a logical 1 might be represented by 5 volts, and a logical 0 might be represented by 0 volts. Refer to Figure 1.6 for a visual representation of a binary digital signal. Here, you see the signal switching abruptly between high, logical 1, and low, logical 0, levels. This switching creates a square wave pattern. The key characteristic of digital signals is this distinct separation between different levels, which makes them less susceptible to noise and more reliable for processing and transmission in digital systems. Understanding the interface. When working with mixed signal systems, we often need to convert between analog and digital signals. This is where analog to digital converters, ADCs, and digital to analog converters, DACs, come into play. The ADC converts continuous analog signals into a digital format that digital systems can process, while the DAC does the reverse, converting digital signals back into continuous analog form. Figure 1.7b illustrates a sampled version of an analog signal, which is the first step in the analog to digital conversion process. Here, the continuous analog signal is sampled at specific points in time, and each sample is converted to a discrete digital value. This process is essential for digital systems to interpret and manipulate real-world analog signals. In digital electronics, we often deal with binary signals. Here, a logical 1 and 0 are represented by two distinct voltage levels, for example, 5 volts and 0 volts. As technology advanced, systems started using lower voltages to reduce power consumption. It's also worth noting that binary voltage levels can be negative or bipolar, as seen in the emitter-coupled logic (ECL) family, which uses negative voltages. Analog signals, unlike digital ones, are continuous and can represent a wide range of values. For example, the voltage output from a temperature sensor can vary continuously to reflect temperature changes. These signals are processed by modifying their amplitude, phase, and frequency. Amplifiers are key components used to achieve the desired signal characteristics in analog systems. To bridge the gap between analog and digital worlds, we use converters. A digital to analog converter, DAC, converts digital data into a continuous analog signal, which can then be used for control or display purposes. Conversely, an analog to digital converter, ADC, transforms continuous analog signals into digital data, allowing for easy manipulation by digital systems. Understanding these converters is fundamental for designing mixed signal systems. Now, let's discuss a structured approach to solving problems in electronics design. This methodical approach helps ensure that we tackle problems comprehensively and effectively. We'll go through each of the 9 steps in detail. 1. State the problem clearly. The first step is to understand and articulate the problem. Write down a clear and concise problem statement. This helps in defining the scope and objectives of what needs to be solved. 2. List known information and given data. Gather all the available information and data related to the problem. This includes values of components, circuit diagrams, and any specific conditions given in the problem statement. Having all the data at hand helps in forming a complete picture of the problem. 3. Define the unknowns. Identify what you need to find to solve the problem. These are the variables or parameters that are not given and need to be determined. Clearly defining the unknowns helps in setting specific goals for your analysis. 4. List assumptions. Make reasonable assumptions to simplify the problem. For example, you might assume ideal components with no losses or perfect connections. Listing these assumptions is crucial as it affects the accuracy and applicability of your solution. 5. Develop an approach from alternatives. Think of different methods to solve the problem. This might include analytical techniques, simulation tools, or practical experimentation. Choose the most appropriate approach based on the problem's nature and available resources. 6. Perform analysis and draw the circuit. Conduct a detailed analysis using the chosen approach. This often involves mathematical calculations, circuit simulations, or hands-on testing. Draw the circuit diagrams clearly, label all components and variables, and show the connections. 7. Check results for consistency. After completing your analysis, review the results to ensure they make sense. Verify the calculations, check for any errors, and ensure all unknowns have been addressed. Consistency checks might include comparing against known values or physical principles. 8. Evaluate the solution for realism. Assess whether the solution is practical and realistic. Consider if the solution can be implemented with available components, if it meets the design criteria, and if it operates within the expected parameters. If not, revisit your assumptions and analysis. 9. Use computer-aided analysis, e.g., SPICE. Utilize simulation tools like SPICE to model and verify your solution. These tools can provide detailed insights and help validate your results. Compare the simulation results with your analytical solution to ensure accuracy. Now for your assignment. I want you to design a simple digital to analog converter, DAC, circuit on a breadboard. I'll provide you with the necessary components and a schematic to guide you. Once you've completed the design, write a report explaining your design process and observations. This assignment is due in our next class session. This hands-on activity will reinforce your understanding of the concepts we've covered today.